Residence time is an incredibly powerful concept to be thinking about as we start to talk about greenhouse gases and their effect on planetary temperature. It's also something that you're going to be thinking about as we move through the course and we start to think about possible ways to offset greenhouse gas emissions. So it's really important to have a good handle on what it means and also how it can be estimated. So we're going to begin with an example, and this is something you can try at home if you want. Don't waste a ton of water, but it might be sort of fun to play around with. This is as if you had a kitchen sink, and you can see that there's water coming out of the faucet, and there's also water leaving the sink by the drain. If you turn up the faucet high enough, and again, I'm not suggesting you waste a ton of water, but if you turn up the faucet high enough, you'll notice that you'll actually get a certain amount of water accumulated in the sink. It might take a couple of minutes, but after a couple of minutes, the height of that water in the sink is going to stabilize. So you've got an input, you've got an output, that's the drain, and you've got a volume of water in the sink. And if you were to actually go ahead and put this on a chart, once it's reached this sort of stable position, the volume of water in that sink over time would remain level. So this tells us that this is a system in equilibrium. So if it's in equilibrium, that means that the inputs are going to equal the outputs. And this is an important fundamental assumption that we're making when we're talking about residence time. We're assuming that we're talking about a system that's in equilibrium. So for demonstration purposes, the residence time that we're talking about is, in this example, if you follow a single drop of water as it enters the system, the residence time is how long this water is actually spending in the sink. And so I'll show you, you can actually, it's pretty simple numerically, so you can actually go ahead and if you have a couple of numbers, you can estimate this. So in this case, the residence time of this sink system is going to be the volume of the sink, so how much water it's holding here when it's in this equilibrium state, this volume, and we'll use the input rate, but it actually doesn't really matter. You could use the input or the output, right? Because since it's in equilibrium, those are the same. So let's just throw some numbers in here. For example, if the volume of your sink or the amount of water that was sort of staying in your sink was 6 gallons, and you knew that you were adding water at 2 gallons per minute, right away you can see that the gallons, that's going to cancel out and you're left with just minutes as a unit, and that's good because we're estimating a time. So what this is telling us is that the residence time of this sink is 3 minutes. So the amount of time that your water particle is spending in there is about 3 minutes. Okay, let's think about this just as a slightly different example, and then we'll look at how this plays out in the real world. But we can also think about this in terms of your bank account. And so if you're earning if you're earning money every month, and that equals what you're spending, so your earnings equal what you're spending, then your bank account is an equilibrium system. And hypothetically, that also means that there is some balance, some bank balance that you're maintaining. So we can think about this again as a residence time. If the balance is $500, so that's the amount that's in your bank account. That's like the volume. And if you're earning, let's say $250 a month, then this is your, I'm going to call it a flow rate. You might also sometimes when you're reading some earth system stuff see this referred to as a flux, but we'll call it a flow rate. I think that's a little bit more natural, and you can think about it as money that's flowing into your bank account. So then the residence time for money in your bank account would be estimated by taking that $500, dividing it by $250 per month, and that indicates that the residence time of money in your bank account is 2 months. It's the exact same idea. It's just applying it to a slightly different situation. So let's think about how this applies to the Earth system, and especially to carbon, since carbon dioxide is a greenhouse gas. There are lots of sources of carbon, especially things like anthropogenic emissions, but that's not the only one, and sinks. And these are places where carbon can be stored. And depending on the flows of carbon in and out of these sinks, some of them have different residence times. So this is one place that we can start to think about this. Just for example, a couple of carbon sinks, we'll talk about vegetation in a second, but vegetation serves as a carbon sink. Soil serves as a carbon sink. Rocks, some rocks, especially those that form in the shallow ocean, can serve as carbon sinks. And the ocean itself, there is carbon stored in both the surface and in the deep ocean. And carbon is flowing between these different sinks and the atmosphere. So it's being exchanged between the ocean and the atmosphere and vegetation. And as I'm drawing all of these arrows, I hope that you're getting the impression that we can start to think about this in the context of residence time. So let's run through one example, and you can see that I've drawn a tree here. So I'll share some numbers with you that are estimates for vegetation, and we can consider that as a carbon, some people refer to this as carbon reservoirs or a carbon sink, and think about the residence time there. So, and again, we're making the assumption that this is in equilibrium. So if we want to consider the residence time, I'm going to abbreviate it. The residence time is going to be equal to the volume divided by the flow. And so in this case, the volume, global volume of vegetation that's taking up carbon is about 560 gigatons of carbon. It's a lot of carbon. There is so much stored in vegetation. What's really interesting is that there's also a pretty high flow rate. And that is estimated to be 123 gigatons of carbon per year. So if you run the math on this, the residence time that's estimated globally for vegetation turns out to be 4.5 years. Of course, if you look at an individual plant, it can be different. So this is just a global average, and it's useful to think about where things might be stored in a relatively short term. Vegetation tends to have a shorter residence life versus places like the deep ocean. Just for comparison, I don't have the numbers on hand. I can find them though and look them up. But the deep ocean has a much bigger volume and has like way bigger, and has a little bit, I think, smaller flow rate coming into it or through it. And because the volume is so much bigger and this flow rate is a little bit smaller, that means that it has a really long residence time. So it's interesting to start to think about, if we have an issue with carbon in our atmosphere, are there other places that it can be moved around and temporarily stored? What's the best way to help manage this? So this is a pretty important concept when we're talking about residence time, and especially thinking about carbon and carbon storage, because some of the solutions that we'll look at later this semester have a different time frame than others. And understanding residence time and how it's calculated is fundamental to sort of thinking about this.